hear me, Dan?
Yep.
Okay. Thank you for having me, and also thank you for coming here. So today we are going to learn about gravitational wave cosmology. I've divided my talk into several parts. And first, we are going to go over the current gravitational wave detection efforts. Then we will talk about basics of Hubble constant measurement with gravitational wave standard sirens. After that, I will update with you the status of Hubble constant determination. One is the first Hubble constant measurement with gravitational waves from GW 1708-17. And my mouse is not working, so I will just tell you where to look at. And then we will see the constraints on Hubble constant with advanced LIGO and Virgo's first two observing runs. And after that, I will talk about the sources of systematic errors for cosmological constraints. And in the end, we will talk about the future projections. First is a mock data challenge with LIGO and Virgo detectors using binary neutron star mergers, and then followed by a brief introduction of estimations with future generation detectors. There's a lot of content there, so I pick up the essence so that people can learn after the talk. And I wanted to say that if you have any questions during the talk, please feel free to interrupt me and ask. So the existing ground-based gravitational wave detectors. First, on the top panel, it shows the two LIGO detectors, and the existing ground-based gravitational wave detectors use the Michelson interferometry. So it has two arms, two identical arms. And for the LIGO's two detectors, each arm is 4 kilometers long. And one is, if you look at the middle picture in the top panel, you can see that the two detectors are located in two sites. One is the LHO, one is called the LHO, it's LIGO Hanford Observatory, and one in the south, the LIGO LLO, the LIGO Livingston Observatory. We collect data using these two detectors so far. And there is also a third LIGO detector. It is in India, and it will come online soon. And if we look at the bottom left figure, it shows the Virgo detector in Italy. It still uses the Michelson interferometry. So it's also L-shaped, perpendicular to each other, the two arms, and they're identical arms. Each arm is 3 kilometers long. And the Virgo detector joined to collect data in July 2017. So it's in close to the end of the LIGO's second observing run. And if you look at the bottom right figure, it's the Kagura detector in Japan. Still the same interferometry principle, and it joined in to collect data in 2020. So with these detectors, we have detected quite some gravitational waves. Now let's take a look at the first direct detection of gravitational waves. It has the designation of GW 150914 because it's detected on September 14th, 2015. And at the time, I was a graduate student at UWM, and we were analyzing this data, and people have had many people in the collaboration thought it might be a conspiracy, whether people made a joke or something, but we just checked the collaboration check. And in the end, we were convinced that the detection was a real gravitational wave signal, was really a gravitational wave signal. And if we look at the this plot on the left, oh, my mouse comes back. So if we look at this on the left, this shows the time, frequency representation of the data. On the left, it's the Hanford data, and on the right, it's the Livingston data. And we know that if we look at this Hanford data, as time goes by, there is changes in the frequency, and we know that frequency is like pitch, the pitch of voices, and we can convert the gravitational wave signal into audible, like into audios, as the human hearing range is 20 hertz to about 20,000 hertz. So we can convert these into something that's audible. And as time goes by, the frequency goes up, which means the pitch goes up. And we saw similar thing on the Livingston detector as well. That makes us certain that the signal comes from the outer space, because there are many noise sources around the detectors. But if we see the same thing in the two detectors that are 3,000 kilometers away, then we know that it's not something local, it's something from outer space. And this figure shows the localization, or the sky area where the gravitational wave source could be located. This was during the first observing run, and only the LIGO Hanford and LIGO Livingston detectors were online. So the localization was like triangulation with two detectors. We got a belt, and here we got a banana-shaped this area here. It's about 500 square degrees. There are a lot of galaxies and stars in there, so we don't really know which galaxy or star this gravitational wave was from, but at least we know that it's from southern hemisphere. And then I'm going to show you a simulation of this gravitational wave. You can see that two black holes are orbiting around each other, and as time goes by, and they are in spiral around each other, and then eventually they merge. And after they merge, there's still these wiggles in the space-time, so there's still gravitational wave there. This gravitational wave lasts only about 0.1 second, so it's really fast. And the sound it made was a chirp sound. It's like whoop, and depending on the masses of the two black holes, the pitch could be different. So this is the sound for a 30 plus 30 solar mass black holes merger. And then we had detected several more gravitational waves in the second observing run, and one of them was a unprecedented event. It's like we were super lucky to got this event. It's on August 17th, 2017, and it's a gravitational wave from a binary neutron star merger. And so on the left, this is still a figure that shows the time frequency representation of the data in 3 detectors, and the LIGO-Hanford, LIGO-Livingston, and Virgo. And on the right, it shows which galaxy it was from. As I just mentioned, the sky localization is like triangulation. With 3 detectors, we can hear better, and we can get a smaller sky area where the gravitational wave could be from. And for this particular case, it was from a region, and people they pointed the electromagnetic astronomers pointed their telescopes into that area of the sky, and they found this optical image. And if we look at on the right, sorry, my mouse is gone again. If we look at the right figure, it's the afterglow of this event in the galaxy cluster called NGC 4993. And we can see that in different days, the optical image went dimmer and dimmer. So in the center, it shows the galaxy NGC 4993. Okay, so with the determination of this galaxy, we were able to determine the redshift using the electromagnetic observations. Here I also list the existing gravitational wave detections, the public ones, of course. So these were the detections we had before October the 1st, 2019, which is which contains the 01, 02, and 03, the first half of 03 observing runs. And we know that in the first observing run, we detected 3 BBHs. In the second observing run, we had 7 BBHs and 1 binary neutron star merger. And in the first half of the third observing run, we had 39 events. So this is a figure that shows the masses of those events. Each, if we look at this individual event, each has 2 smaller black holes or neutron stars, and then they merge into 1 bigger black hole, or could be, in some cases, could be binary neutron star, sorry. So that's that. And then with these background, with the background knowledge, let's take a look at the Hubble constant measurements. We know that for a nearby universe where the redshift is much smaller than 1, we can use Hubble's law to measure the Hubble constant, where the Hubble's law states that the velocity or the recession velocity v is equal to the redshift times the speed of light equals the Hubble constant times the distance to that event. So we know that we need 2 ingredients to determine the Hubble constant. One is the recession velocity, or the redshift z, and this is from electromagnetic counterpart. This usually comes from the ENM observations, but I'll make a start here to just to remind people that there are also proposals to use mass distribution, equation of state, etc. method to measure the redshift with gravitational waves only. So in the future, there's gravitational wave cosmology that do not require input from electromagnetic observations at all. And another ingredient is the distance. So we have basically 2 ways to measure the distance to something. Traditionally, we can measure the distance using this cosmic distance scale or the ladder. We build up a ladder to measure the distance to objects, celestial objects. And we call these standard candles. Now we have another way to measure the distance to something. That is the gravitational waves. And we call them the standard sirens because we kind of hear them and people make an analogy, call them standard sirens. And there are 2 kinds of standard sirens, the bright ones and the dark ones. These are the words that we use to describe the situation that for the bright ones, we observe the electromagnetic counterparts. So we observe some ENM emissions. And for the dark ones, dark standard sirens, we don't see any electromagnetic emissions. And for those ones, then how do we measure the Hubble constant? Well, because we're gonna lack the information of the redshift. And for that, I have this figure on the bottom left. It's a piece of bread with raisins in them. If we think the bread as the universe and the raisins as the galaxies in it, then if we have the information of the redshifts of all of these galaxies in the universe, then we can use these redshifts as prior information of where the gravitational wave source could be. So that we can also come up with a method to determine the Hubble constant. I will talk about that later. Okay. We know that for gravitational waves, to measure the Hubble constant, it is important to get the luminosity distance. And here I show the equation that gave the relation between the luminosity distance and the other parameters. So if we just look at the first half, like the first half of the equation, d is the luminosity distance to a gravitational wave source, and h is the detector strain and dimensionless amplitude of that gravitational wave. Notice that this detector strain is very small. It's recorded by the detectors. It's the stretch and squeeze by the gravitational wave to the detector. And it's usually on the order of 10 to the minus 21, that small. If we can record this information and with also the f, the chirp frequency of the gravitational wave and the changing rates of chirp frequency, then we can determine the distance to a gravitational wave source. We don't even need a ladder, like we don't have to build up a ladder. So I just want to briefly talked about this gravitational wave standard siren. So it is a gravitational analog of standard candle, and we can hear it, like convert the frequency into human audible audios and hear them. And we know that the strain, I just said we measure, the detectors record the dimensionless strain, and this strain is expressed in this equation, and the equation is determined by the chirp mass or redshifted chirp mass and the chirp frequency and the distance, and also a bunch of angles and the phase of the gravitational waves. So from there, just show again how we could determine the luminosity distance. It is a direct and independent measurement of absolute distance, and there is no distance ladder needed. It's calibrated by the general relativity. This was first pointed out by Bernard Schulz in 1986. Okay. So historically, people have measured Hubble constant like many times, and till now, since over 100 years ago. But recently, there's the measurements that sort of converging, but still not consistent, very consistent with each other, and we call it the Hubble tension, or the tension over Hubble constant with electromagnetic wave observations. And this is only the with the electromagnetic waves. And we can see that the discrepancy can be as large as 4 sigma between the early universe observations, like the measurements constrained by the early universe observations and the late universe observations. And the early universe is through the cosmic microwave background observations, and for the late universe, it can be supernovae, Cepheus, or the tip of red giant branch. So this tension needs to be solved, and because gravitational waves can provide independent measurement of the distance, we might be able to solve this tension, solve this discrepancy. So let's take a look. This is the first gravitational wave standard siren measurement of Hubble constant with GW 170817. Apologies for this. And recall that it is the first binary neutron star merger that's detected. And because we also observed its counterpart, we say it's a bright standard siren, and we measured the Hubble constant. On the left, I showed the sky localization. So you can see that it's in a very small sky area. There is results from LIGO alone and LIGO and also from Fermi and other observations. And when we put each other as the prior information to each other, and then we came up with this very small sky area by area, and that included the NGC 4993. But we also concluded that it was from the NGC 4993. Sorry, and with the redshift obtained from electromagnetic observations of this NGC 4993, we estimated the Hubble constant. The result is shown on the right. So we can see the green vertical lines, or the green shaded area, the orange lines measured from the gravitational wave. And then we have this result. The result is, the estimation is 70 plus 12 minus 8 kilometers per second per megparsecs. This is at about 15% accuracy. And it's the mode is 70 kilometers per second per megparsecs. This is a little bit diplomatic for the results, considering the Planck and Schutz results. So it's not offending anyone, but it's what we get. So this result is consistent with existing result, but still we cannot exclude any of the, either of the Planck or the Schutz, because we only have used one event. If we have multiple events, then we can make the measurement accuracy better. I will talk about that later. Okay, so we just talked about the Hubble constant measurement with bright standard siren. Then how about the Hubble constant measurement with dark standard siren? Because as we just saw in the first 3 observing runs, most of the gravitational wave events are BBHs than the BNSs. In most cases, we don't have the EM observations. Then how do we make use of these BBHs? By which I mean binary black hole mergers. So this is the gravitational wave dark standard siren measurement of Hubble constant with GW 17. Oh, my mouse comes back. 170814. In this case, we only knew it's a binary black hole merger, but we didn't know which galaxy it was from. On the left, we have the dark energy survey, DES galaxy distribution for the galaxies surrounding or in the sky localization area of the gravitational wave. As I mentioned earlier, each galaxy or each region in that bread has its redshift information, and the gravitational wave can be from one of those galaxies, even though we don't know which one it is. But then we can use that as the prior information and integrate those to get the Hubble constant measurement. For this event, we have an estimate of Hubble constant of 75.2 plus minus 40, around 40 kilometers per second per megparsecs. Note that this is larger than the bright standard siren measurement with GW 170817. So that this is from a single event or from a single binary black hole event. If we have multiple events, then we could do better. Now, let's take a look at what we had with the first and second observing runs. So this figure shows the estimations using the when I say BBHs, this binary black hole modules. Each line shows the individual estimate, similar to what we had with that GW 170814 binary black hole module by the LIGO collaboration, and this one by the LIGO and the dark energy survey. Each line shows the measurement with one binary black hole module. And you can see that each individual one is not accurate enough compared to the bright standard siren method. But for Bayesian analysis, we can treat each measurement as the prior of another measurement. So we can combine all these measurements together and see what we can constrain. This is the result we got with the combination of multiple events. So this orange line in the middle shows the GW 170817 counterpart, which was shown earlier. And the blue line showed the red line showed the joint binary black hole measurement. So lost my mouse again. So if we combine all these measurements together, we got this sort of the horizontal line there, where we don't really have much information about the Hubble constant. We only had a little bit because the posterior, this posterior distribution is flat, is sort of flat, only a small, like a bump there, a big bump there. And combine the binary black hole with the binary neutron star measurement, we got the joint binary black hole and the binary neutron star with counterpart measurements, which is shown in the blue line. And you can see that because the y-axis is the posterior value, and the larger the posterior value means we can constrain it better. if we compare the BNS measurements of the binary neutron star measurements with the joint BBH and BNS measurements, we can see there's only a little difference, and the blue line just goes up a little bit. Its distribution is a little bit narrower than the BNS measurement alone. So that's the update from update or the improvement with the BBHs. With more events, we will keep updating this plot, this blue line. It will go up and will become narrower and narrower. And eventually, at some point, we will see which observation it will be more agreed or exclude out the Planck or the choose the CMBs or the supernovae observations. So that's about this figure. Then I'm gonna briefly talk about the systematic effects and statistical errors of Hubble constant measurements with LIGO, Virgo, and Kagura detectors, which we call LVK. So first, there's the systematic effects due to the photometric measurement of redshift. It's smaller than the current statistical uncertainties, but it should be treated with increasing gravitational wave detections. This is not quite the problem for LVK detectors. It's more on the electromagnetic observation side, but to use the distance measured by the LVK detectors, we also need to keep this in mind as we have many more detections. And the second is the systematic effects arising from limitations of waveform models, which were restricted to quasi-circular orbits and neglected some advanced physics, such as the higher modes, the precession of the spins of the black holes, etc. We do have models to do that now, but we are like improving the waveform models. And this is currently not a problem, but it will be when the number of detections lead to small uncertainty in H0. So this is being investigated. And another systematic and statistical errors are the calibration error. So for the gravitational wave detector calibration, for now it's around the 2% level. I know it's less than 4%, but it will be a problem when we reach 1% level Hubble constant measurement with many gravitational waves. So this is being investigated in the collaboration as well. This is something that's kind of difficult to get rid of because it's related to the detectors, but we are improving the detectors. So that's about that. And we also have a small systematic and statistical errors from the parameter estimation on the luminosity distances of those gravitational waves. We know that for the gravitational wave inferences, the estimation on the distance is currently at 20% level accuracy, and there's some systematic bias, like for all the gravitational waves, they could shift toward one end, could be like all of them are smaller than the true value. We are doing injections and doing those studies to see the effects from the parameter estimation and see how much it will affect the luminosity distance measurement. But like I just mentioned, these are small errors. It will become a problem when we have many detections that make the Hubble constant measurement very, very accurate at 1% or a couple of percent level. Okay, so then let me talk about the future projections. We have this, I'm gonna briefly show you this mock data challenge we had in the collaboration with 249 binary neutron star mergers in the O2 or the second observing run scenario. So this figure shows the Hubble constant measurement from MDC0. Briefly, I use that name, but it's the counterpart case. Suppose for each binary neutron star merger, we can we know where it's from. Because it's mock data challenge, we injected these binary neutron stars into some certain galaxies, and we just assume that in observations, we observed those binary neutron stars from these galaxies, so that we know the redshift information. And we can use the bright standard siren method to get the individual estimate of the Hubble constant with each of these binary neutron star mergers. And the lines, the thin lines shown in this figure are these individual estimates of Hubble constant. And combining all of the 249 events together, we got this value. We got this orange posterior or estimation. And the vertical dashed line is the injected value, where we assume the universe has a Hubble constant of 70 kilometers per second per megparsec. And then we recovered the estimation. We also did the standard, the dark standard siren case, where we assume that for none of the binary neutron stars, we detected their or we observed their galaxies. We don't know where they were from. So for each binary neutron star, it's like a binary black hole because it only has the distance information and we don't know its redshift. And we use the galaxy catalog as the prior information. Then we have estimates of the Hubble constant. And here we assume that the galaxy catalog is complete because we know in real observations, some of the galaxies can be missed. It's usually not a complete galaxy catalog, especially as the redshift goes up. There's more galaxies and it becomes less and less complete. But in this mock data challenge, we assume it's complete. And then we have these results. So we also studied the scenarios where the galaxy catalogs are not complete. Here it shows the 100% complete galaxy catalog case, and then followed by the green lines are the 75% and the 50% and then 25%, and also the counterpart case where we know the redshifts. So this shows the Hubble constant estimation as a function of number of events. We can see that the Hubble constant measurement uncertainty scales as the 1 over square root of n. If the number of gravitational wave events goes up by a factor of 4, then we get the uncertainty halved. So we get better Hubble constant measurement uncertainty by a factor of 2. So that's about that. And then I'm gonna briefly talk about the some of the next generation detectors and precision cosmology. So, I forgot to mention here with those 249 events, we can reach a Hubble constant measurement at 1 to 2% level. If we look at this purple lines on the bottom, or the other lines on the bottom, we see that it reaches a few percent level accuracy. So then let's take a look at some of the next generation detectors. On the left, we have the Cosmic Explorer. This is planned in the United States. It's still using the Michelson interferometry. And each arm of that L-shaped detector, each arm is 40 kilometers long. Recall that for LIGO, the arms are 4 kilometers long. So this is a factor of 10, and its sensitivity is significantly higher, and it can reach to deeper, to the detections of gravitational waves in deeper space. I didn't mention for LIGO, LIGO, Virgo, and Conqueror detections we had so far, the furthest we had is at a redshift about 0.8. So for Cosmic Explorer, it can go further. And on the bottom left is the Einstein telescope. It's a plan or proposal in Europe. I know it's also like it will also be online in the next decade also. And each arm is 10 kilometers long. So on the right, I showed the figure about the LISA detector. LISA is a space-borne detector. It's a space antenna. And it also uses the interferometry, Michelson interferometry. So it's a collaboration by ESA and NASA. It's planned back in 1990s and early 2000, like before 2011. Those two work together, but in 2011, NASA dropped, and only the ESA or ESA was working on that. But recently, NASA was back, like they got this proposal online, got the funding, etc., and they are working with ESA together again. So the detector is 2.5 million kilometers long for each arm, and it has 3 arms, so it's like 3 detectors. And in the end, I just briefly show the detections of gravitational waves as at higher redshifts. For example, for LISA, it can reach to a redshift larger than 10. The Hubble parameter and other cosmological parameters will be constrained. For now, with LIGO, Virgo, and Cardiff, we only constrain the Hubble constant, which is the Hubble parameter at redshift equals 0. But in the future, we can explore other parameters, estimate other parameters as well. For example, I listed a few papers here. Due to the time limit, I just could not go through their results, etc. But I think it would be beneficial for me to put here for people to take a look. So with LISA, we have this estimation from Tamanini, and with Einstein telescope, we have estimation from U, etc. And with the advanced LIGO plus, which we call A plus, and Voyager-like detectors, as well as the Cosmic Explorer-like detectors, Chen, etc. They had estimations of Hubble constant and the cosmology in that paper, if people wanted to look. And in the very end, I show this gravitational wave spectra here. So it's like it spans from very small hertz to very big hertz. And on the right end, we have the LIGO detectors, which have already detected gravitational waves. And then the longer gravitational waves, which I mean in wavelength, the longer gravitational waves can be detected by LISA. And next, even longer gravitational waves can be detected by pulsar timing. And even longer gravitational waves can be detected by cosmic microwave background polarization. With the detections of gravitational waves, we will be able to do many interesting astrophysics and astronomy. So just get prepared. So that's my talk. Thank you so much. I hope you enjoyed it.